Okay, welcome everybody for our it's May, right? FPGA seminar. And so I'd like to thank Brian for coming. This one's, I guess, not just a paper, it's kind of a tutorial in a sense for something I think a lot of us are interested in learning a bit about. So well, thank you, Brian. And it's all yours.
Thanks. So as Professor Chow mentioned, my name is Brian, and I just finished my PhD here, and most of my research was in developing algorithms for automated debug. But I thought that would probably be pretty boring and might go over your head in some sense. So over the years and during my graduate school, I picked up a lot of stuff on how to do functional verification and debug, talking to a lot of people in the industry. And this presentation summarizes a lot of the important concepts that I think are important to know. And as you'll see, I stole a lot of slides from other presentations that I've seen. So I think there's a lot of good information in there. And hopefully, I can get you guys a little bit motivated to maybe doing some more functional verification on the FPGAs, because I know it's not as pervasive as it is in the ASIC world or the actual chips. Okay, so without further ado, so since this is, I say overview in the title, and it really is an overview. So what I would like to encourage is, if you have a question on a particular slide, maybe raise your hand, and then we can talk about that topic a little bit more, because really I'm not going into any deep depth in it, and I can kind of give you whatever I know about it if you have a question beyond what's on the slides. Okay? So as I said, my research is in debugging, so I just want to start off with this quote that I saw another Harry Foster show at one of the conferences I went to. And it's by Brian Kernighan. It says, "Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it." And I think this is really good advice to everyone, maybe especially graduate students who are trying to come up with something really clever, right? Okay. So this talk just basically has 3 parts. I'm going to try to motivate and give some background about what functional verification is, what debug is, and some trends to motivate you why this is an important topic. And then the second part is just tools and technologies. I'm just going to go through one slide each through a bunch of tools and technologies that we use in functional verification. And then the last part is a more interesting part too. Functional verification is not just putting a bunch of tools together and using them. There's a lot of process and methodology involved. And there's a couple, 2 or 3 interesting ideas that I'm going to present in the last part, which I think won't be too unfamiliar to many of you. So here is a really, really simplified version of the design cycle, and I think many of you are familiar with it. We start off with the specs, go to RTL, somehow get the physical design, then we make a chip and then ship it to the customer, right? So this is kind of what we're taught in our digital design course. Yes, this is kind of how it works, but really something more accurate is this. We're missing this really big step of testing the chip to make sure it works, right? Because we're not going to ship something unless it actually works. So before we actually take our RTL, we have to test it. And usually when we test our RTL, the term we use is called verification. So at the logic level, we're ensuring that functionally it works as we expect. And then there's a corresponding term over here on the actual silicon, which we call test. So just to distinguish between these 2 parts of which part we're actually testing, we use verification and test as contrasting them. But of course, our first iteration, our RTL, is probably not correct. So what we end up having to do is, after we detect a failure in verification, we've got to do some kind of debug and kind of loop back and forth, maybe change some of the RTL too, and we keep going in this loop until we figure out, until we kind of reach some point where we say our RTL is good enough, and then we move on. And then similarly, there's a corresponding thing in the silicon, and this is a whole different topic, which I won't really touch on. I'm really just going to be touching on this first part here of how to do this front-end verification of RTL. So, for the FPGA guys, right? We just replaced the chip with the FPGA. So, why should we care about this RTL verification, right? There's all these other issues like power, timing, crosstalk, analog effects. But it turns out, this is a study headed by Harry Foster at Mentor Graphics. They asked like a huge bunch of customers all around the world. And it turns out, even though the trend of logic or functional bugs is going down, it's still a significant portion of the reason why chips need to be respun. So this graph is basically saying about 50% of the reason of why respins happen are because of logic or functional bugs. And these are bugs we should be catching before we send masks to the fab. We should be catching them in the RTL. So this kind of gives motivation why we need this functional debug. And so just to give you some more motivation of why we want to find them during RTL simulation and not maybe sending them to the FPGA chip and then debugging it there, we can just look at how long it takes to debug at certain points. So this first point is when you're actually writing the RTL. When you're doing RTL design, if you find a bug, it's pretty easy to fix. You have the whole context of what you're writing there, and it probably will take in tens of minutes to fix. It's pretty quick. The second stage of finding a bug and fixing it is probably during RTL verification. And what this step is after the designer has written the RTL, he usually ships it to a verification engineer or kind of a test engineer, and he's going to run intensive simulations on it. Now, once a bug is found at that point, it gets a bit more complicated because now the verification engineer doesn't know the design very well, has to find the right designer. It might have more than one design block, and at that point the designer may have moved on to a different block, doesn't remember exactly what he wrote. So in terms of how long it takes to fix, it could take hours in some cases. Now, at the third point over here, and this is kind of when you're putting your whole system together. You're putting all the design blocks that you have, and maybe you have an SoC, or maybe you have a huge FPGA chip over here. And typically what people will do is either, emulation I think is more common, but basically put the whole system on some kind of thing that we can execute really fast. So that could be an FPGA prototype of the system, or one of these really expensive emulation boxes. And this is like a real pain to debug because you have so much less observability, and the thing could run for millions and millions of cycles before the bug is found, making it incredibly hard to debug and fix. And then, of course, we can't forget the last point over here where we actually have the silicon chip and we find a bug in it. I mean, this is like almost impossible to debug. I've heard stories of, take 3 months to find one bug in a silicon chip, right? So this is really, really costly. And so the idea is, as much as we can, we want to find bugs closer to the left. And so an ideal curve of what we want to find is something like this, where most of the bugs that we want to find, for practicality reasons, should be in RTL verification when we're doing RTL simulation. And obviously, we won't be able to find every single bug just because some bugs only appear after we integrate the system. So hopefully we can find the next majority of system integration bugs when we're actually doing this FPGA and prototype emulation. But the idea is that we should be finding all the possible bugs we can at the RTL level, and then only when we do system integration we find system integration bugs. And hopefully we're not going to find any silicon bugs, but there's always things that we won't catch. So these are some numbers from Mike Stelfox at Cadence, and this was basically a survey of Cadence customers, more advanced Cadence customers. And so this is talking about front-end design, the RTL design process. And you can see functional verification takes 60% of the total design and verification time. And you see how much design actually takes 20%. So these advanced customers are spending more and more time on functional verification just simply for the reason I stated before. It's too costly to not do this functional verification. So there's a tremendous amount of effort in functional verification. And of this functional verification time, debug is actually one of the biggest components. And that's where my research is focused, or was focused, as I said before. So these two problems are really, really big. And maybe you're not exposed to it as much in the FPGA world, but I think more and more this is trending, and I think I have a slide on that. So this is a kind of funny slide that Harry Foster had in his presentation. So obviously, after 2017, these are estimates, but you can see in 2007, around almost 50% of the time was spent in verification. In 2012, even more time was spent in verification. And the funny thing is, if this trend continues, eventually we're going to have 100% of our time in functional verification, which obviously is not going to happen. But you can see that the point is still interesting, that we need to do something about this functional verification, right? We need to do it better and do it more efficiently. Okay, so this is more interesting for these FPGA folks here. This is from the Harry Foster survey, again, of FPGA customers. And you can see the first column is functional simulation at the RTL level and code coverage, which is something I'll talk about later. But basically, you can see there's a trend in terms of more and more people are starting to actually do simulation at the RTL level, and more people are actually starting to use code coverage. And I think the problem is not as amplified as it is in ASICs, but basically I think FPGAs are seeing the same trends that we had in ASICs, and so people are using more and more of these functional verification techniques when doing FPGA designs. An interesting point here that I thought of is that this isn't 100%. This number is definitely 100% in the ASIC world, but is not in the FPGA land, which I find interesting. I think sometimes, for sure, you don't need to do RTL simulation if it's an easy design, but I would think this number should be much, much higher. And then this is the last part of the motivation. When we think about our verification, you can think about efficiency and effectiveness. So this dotted line you can think of as like 100% verification, ensuring your chip is correct. And the idea is that our verification strategies, it should be more efficient, that is, take less time, so we want the curve to the left, and we want it to approach this asymptote as fast as possible. And so with a lot of the stuff that we learned in kind of undergrad classes, just using simulation, it's very difficult to approach this. So there's a bunch of techniques that we combine together to basically push this curve to the left so we can have a more efficient verification and get verification closure much, much earlier. Okay, so now I'm just going to go through like a bunch of different tools. And so if you have a question on one of them, please raise your hand and we can just talk about them, because literally I have about 1 or 2 slides for each one. So I don't have much. The first one is, I think, what most people are familiar with, and this is what most people think of as RTL simulation. What you do is you write some stimulus for your design under test. To test some particular functionality, you run it, and then you run it through the simulator, and at some point you check the outputs to make sure they're correct. Right? This is kind of what we all learned in undergrad. And the test bench, basically, you can think of it as, you think of writing a test and checking it, but it kind of implements the specifications, right? You write the test bench compared to the specifications and make sure your design under test works. Now, the real problem here is that it's very labor intensive, right? We got to write, well, think about the state space of the design, how many input vectors you need to cover the state space. It's unwieldy for one person or even a team of people to write all the test vectors you actually need to make sure your design is correct. And this is kind of the point here. Here's an example where if your error depends on a specific address and data value, what are the chances that the stimulus that you write is actually going to test that data value and address, right? Are you going to try to cover the whole address range and data? It's very unlikely. So this is actually kind of deprecated. It's used kind of in some smaller cases, but the next slide is going to be much more really what most people are doing nowadays. And it's called constrained random simulation. So the idea is no longer are we just trying one specific test vector testing the chip. What we're going to do is sort of write a group or a set of test vectors based on certain constraints. And so when, for example, say we want to test a packet through one of our designs, our packet, we can write a constraint that says, well, this packet must have address ranges from XX to YY. And then at that point, what the simulation is going to do is it has a constraint solver inside, and it'll pick a random value between XX and YY, and at that point, it'll send that packet through. And so in that manner, what we can do is run multiple tests and have relatively good coverage by only really writing one kind of test template. And for multiple seeds and many, many different boxes simulating, we can cover a huge amount of state space much more efficiently than if we just ran manual tests. And another interesting component here, we can do much more complicated things. Well, let's say our data is 8 bits and has a parity. Well, we can say 90% of the time I want the parity to be set correctly, 10% of the time I want it set incorrectly. And the constraint solver will match that probability distribution and make sure we're testing a pretty wide variety of data going into our design. Now, the only issue here is that, well, even though if we write a bunch of these templates of constrained random, there still may be a lot of things that we miss, right? Because we can't think of everything just on our first go. So there's something that's usually combined with this, which is in the next slide. Yeah.
So you say the valid address range, but wouldn't you want to test something that's not a valid address too?
Yeah, so that's a good point. I think you can have tests for both, essentially. So one of your test scenarios, kind of the test that you actually write, maybe is this a valid test. And then you may also have one where it randomly picks an invalid address, and you can put a different constraint for that. So I think it can get pretty complicated. And typically, a lot of these things are going to be coming out of your specifications. Like, my design should do this, so you want to write a generic template of a test that tests it, and you want to run it for multiple seeds, as many hours on the simulator as you can.
Right. I guess it's kind of like, often you read the spec and this is what it should do, but you never think of the crazy things that might happen.
That's a really good point. And so the next point I'm going to talk about is trying to cover that deficiency, essentially. And it's basically this idea of coverage. Oh, this didn't come out well. So coverage is basically measuring how many of the design features have been exercised. So this is a really important thing, right? We're testing all this stuff, but how do we know we've actually tested everything? And so coverage is some way of measuring that so that we can have a feedback loop of our directed and constrained random tests, measure how much we actually covered, identify where we haven't covered, and write some new tests to cover those holes. And so this is one of the main ways people decide, am I done our verification? Have I simulated enough? And typically, sometimes these holes that we have here are really hard to hit for different test cases. So this could be this loop could be run multiple times, and it could be really hard in especially later stages to actually cover some of these holes. So those are two coverage metrics, and they're not too surprising. The first one has to do with code coverage metrics. So we can make sure every line in the RTL has been executed once. We can make sure every path in the RTL is executed once. Every bit has been toggled once. Every state has been hit once. And usually, I think they use a combination of these things. The next one is functional coverage. Basically, when we have a specification, we want to you'll write certain properties or behaviors that ensures that are executed. And one example is if you have a finite set of interactions between a design and a bus, you want to make sure every one of those interactions has been tested at some point. And so you can write special behaviors or properties that will run during a simulation, and your coverage tool will pick up and measure that you actually have covered that behavior. So as I understand it, most modern flows will use a combination of both of these to get a sense of how well they've done verification or how close they are to verification closure. Any questions on this? So I think two of the main, constrained random and coverage are probably two of the main things that are going on today. Yeah?
So how would a designer go about choosing what is the right combination to use?
Of these things?
These metrics, yes.
Well, so I don't have direct experience with this, but my guess would be a lot of the tools they'll probably just turn all these metrics on and start measuring all of them. And so they'll just probably put them all together at the end at some point, whoever the manager is, and say, well, how much more do we have to go? And make these decisions probably based on the design and based on their experience. Yeah?
A lot of these things that you're talking about have distinct parallels in software testing.
That's a really good point, and that's actually one of the really interesting points. Hardware designers and hardware design process has not really adopted a lot of these new techniques that actually have been around in software for many years and actually has been adopted by the software community. And I think there's a significant amount of resistance to a lot of these new technologies and techniques just because when you introduce something new, you kind of introduce some uncertainty in your design process. And I think more and more people are moving toward this really because of the necessity, because they just couldn't do it before. You just can't verify the chips that are coming out today.
What languages are people using now to write these test functions?
Yeah, so that's a good point. I have a slide on that. But basically, System Verilog is the most popular that I know about. And the reason is, which I'll show later, is because it natively supports all of these constructs. Before System Verilog, basically we had all these proprietary languages and methods, and test benches were basically the wild, wild west of everything, anyone doing everything of whatever they thought was good. And at the same time, hardware, as I understand it, the hardware community is not as open as the software community. So a lot of the practices that you see at, say, Apple or Intel wouldn't be shared across companies. And I think that's slowly changing, at least by some of the communities that I'm seeing. But I'm pretty sure early on it wasn't the case. So knowledge, I guess, doesn't spread as fast in the hardware design community. Or verification, at least. I don't know. The next thing I'll talk about is assertions. And it really relates to coverage in some sense. And basically, an assertion is like what you think of an assertion in software. It's checking some condition is true. It doesn't fail. And what it really is, if you think about it, it specifies the designer's intent in a property, a formal property, but basically just it specifies in designer's intent on what the design should do. And it's not written in RTL, it's written in this really complicated language, which I have an example below. And the whole idea here is that we can use assertions to increase the observability or how much checking we're doing, the granularity of the checking. Whereas in typical test bench, we'll send some input in, and then the outputs come out, and we check the outputs. There's all this stuff in between that we're never checking, or we don't check immediately. So the whole point of assertions, which, I mean, mirrors software, is really that we're putting all these little assertions in so that we're checking it much immediately after something happens, so that if a bug does occur, it will catch it much, much faster, making it easier to debug, and well, just easier to debug, and maybe we'll catch more of them too. So just to give you a flavor of what some of the power of these assertions, these aren't just kind of immediate assertions of what we're used to in software. They're what's called temporal assertions. And so we can reason about what's going on in the design over time. So we have this spec over here that says if start is active, data repeats 2 times before stop, and 1 cycle later stop should be at low. So this is maybe something you have in your specification documents. And what this System Verilog assertion over here is saying, well, now we're going to sample the values at the pause edge of the clock. And what this says, on the rising edge of the start signal, in the next cycle, we want data to repeat 2 times, not necessarily consecutively. And then 1 cycle later, we want stop to be high, and 1 cycle later, we want stop to be low. So you can already kind of see some of the power of what we can do in System Verilog assertions, specifying these really complicated behaviors, although the language is admittedly a bit too complex in my mind. So over here on the bottom left is just kind of one realization that matches this assertion of what this happens, but there are many kind of different waveforms that will match this assertion. Yeah.
How does that impact the speed of the simulation?
That's a good point. It will generally increase these simulation time, but I think if you're writing them manually, you probably can't write enough to significantly slow it down. There are automated tools to do it. And I think the second point is that most people would say that it's probably a good trade-off in terms of the time you save of catching a bug much earlier and ensuring that your design is, I guess, correct. That's a good question. Anything else on assertions? This is my only slide. Well, talk about it a little bit more. So one thing is we can write them and run them during simulation, but we can also use assertions and synthesize them to our design. And so there's a bunch of work that basically will take a system Verilog assertion, or what kind of assertion you write, and actually synthesize it to logic. Logic that you can put on your FPGA or put on your ASIC or whatnot. And so the whole idea here is the same thing as in RTL simulation. One, increased observability, increased debuggability. Closer to the error, easier to debug. And I think they're used, these kind of assertions are used in Silicon Debug to trigger trace buffers, which will basically record a bunch of the trace of when the bug, close to when the bug happened. But as I read in some articles, that this is typically only used in more advanced processor or SoC designs, just because I think the bugs are much more complicated there, and they really needed it. I think there's probably a lot of overhead, and there's not really, I don't think many tools are really pushing this. So it really hasn't become, at least in my understanding, that mainstream yet. But I feel like if a lot of people are doing debugging on the FPGAs, this could be a really good avenue to help debug and verification, basically. The next thing I want to talk about is formal verification, or model or property checking, which is a lot closer to what I do in my research. And the whole point is we have these assertions or properties that describe what the behavior of the design should be doing. Well, if we know what the design should be doing in some kind of formally or mathematically specified property, why don't we try to prove it about the design? And that's what formal verification is trying to do. Essentially, it's trying to exhaustively check the state space of the design, asking if there are any violations of these properties or assertions. And so an example is, say you have an error pin on your chip, and the error pin should never go high. Well, that's basically a property. And so what we can potentially do is go through every possible state of the design and ensure that error signal never goes high. Now, the important point about formal verification is that it doesn't execute the design. It doesn't run simulation. It actually uses mathematical techniques to analyze the state space of the design and prove, that's why I kind of say prove in quotes, prove that this property can never be true. And so what it's really used for nowadays is good at finding, it's usually used as a bug hunting tool. It's good at finding corner case things that your simulation, your constrained random doesn't cover. But the only problem is writing these properties, running these formal tools requires a lot of effort and very specialized knowledge. And I kind of heard an anecdote that basically they only hire PhDs to do this because it's too complicated for most verification engineers to understand. But I don't know if that's true. And then there's also a limitation, because since we're we're checking the entire state space of the design, it may not be possible for really large designs. Usually this is not done on the system level, it's done on the block level. And then more complicated formal techniques can be done using kind of interactive, what is it called? Like an interactive proof, where theorem proving, to basically prove more complicated blocks, like a floating point unit. They have really specialized people doing that too, like at Intel or AMD. The next thing that is pretty useful are what's called static linting or static checks. And so again, because of the word static, we're not really executing the design. Instead, we're using other methods like formal methods, mathematical methods to analyze the design, or structural methods, looking at the RTL structure or the gate level netlist structure. So there's a bunch of different tools that do this, and they're very useful because, for the simple reason that they're easy to use. You just click a button, essentially, and it gives you a report of what's wrong with your design. So I think these are getting a lot of popularity, and there are a bunch of small companies that figured out that this is a really good use model of formal technology and also just structural analysis, because it's so good at finding bugs very easily with very little effort. So the first one are something that maybe we're a little bit familiar with, just RTL linting. So you can check design or coding guidelines for synthesizability, simulatability, testability, reusability, basically some certain rules of how your RTL should be structured. And I think a lot of hardware design companies will have certain rules that they're checking for. So that's good. Yeah.
That'll be implemented like company to company. You'll say these are like my rules for my
exactly,
as opposed to that company saying this is what good Verilog looks like.
Exactly. Like I know one group in Freescale basically doesn't make flip-flops in the regular way. It always instantiates their flip-flop module, for example, right? So I guess one of their linting checks would be you never instantiated the flip-flop, the regular Verilog way. So I mean, this is really just to ensure that this is kind of a process thing. Coding guidelines are a process thing to ensure that we don't introduce weird bugs, because different coding styles can produce really strange bugs. Especially since the Verilog language was never meant to be synthesized, right? I mean, it's not a very good language. And System Verilog is not very good too, because it's just an extension of that. But there's some other problems. So the next one is like structural checks. So it can check for combinational loops, clock gating issues, and there's a whole bunch of things that we can actually check just by analyzing the structure of the RTL or gate level netlist. And then these formal checks have become more popular, and a good application of formal techniques, because they scale pretty well, is you can check for unreachable states, live or deadlock, stuck at constants on certain signals, dead code. There's all these really cool things that we can check for without actually having to simulate design. And then we have actually a bunch of new tools that are checking really important problems, such as X-related issues, clock domain crossing issues, and power consumption issues, or something along those lines.
What do you mean by X-related issues?
So, in Verilog simulation, you can have multi-valued logic, but you can have 0, 1s, and X's. And so one of the really big problems that a lot of people have, well, there's a few different problems. One is when you just run RTL simulation and you somehow get an X at the output, and you have to trace what the problem is, where the X came from. Because generally you don't want any X's to happen. The second issue that's related to X's that is a really big problem is when you actually send your RTL design to synthesis, you have a gate level netlist, and you just start doing some gate level simulation, you somehow find an X that's in the gate level netlist and not in the RTL. And so basically means it's a mismatch. And usually that problem is related to how you coded the RTL. And there's different semantics of how X's work in gate level and RTL level, they're really weird. It doesn't really make sense why it's like this, but there's like, I can look up like 3 papers that are already talking about X-related issues. It's a really big problem. Yep.
So, FPGA tools already have a lot of these integrated into the flow. Like this is part of just regular RTL compiler, not as a separate link.
Okay, yeah,
Basically,
that makes a
most
lot
of
of
these
sense.
things, especially combinational loops.
They come up as
yeah.
warnings, maybe, something
Yeah,
like
it's all
that?
part of warnings, and you can promote them to critical warnings or errors. Well, most of these. Not the reusability and the stability, things like that, but the other ones below it, like static structural checks, all of that, so it's all part of the tool. Like.
Nobody reads the warnings.
But yeah, and you have control over disabling them manually one by one, or as I said, promoting them.
I think that's really, really good.
So if it seems that in ASIC, if this is not standard, and from what people have told me that in ASICs they're behind in that front.
Well, I would say probably all the tools that you're using that are built into the FPGA compiler synthesis tool are probably already built into ASIC ones. They probably are using equivalence. That would be my guess. I don't know, but that would be my guess. And I know a lot of companies are using these formal checks now just because they find, like, if you have one bit in your design that is always a 1, is that a bug? Well, you don't know, but you probably weren't expecting that one signal to always be stuck at a 1. And so if we use some kind of tools to do a formal check, then you can go investigate what's wrong with that. Maybe it was just a weird side effect and you wanted it, but more likely you did something wrong, right? And I doubt the FPGA companies' tools have that unless they're kind of licensing from a lot of these other companies that are doing these formal
Well,
checks.
they have in Quartus when you compile it says warning output permanently stuck at VCC. It will grab.
Okay. So I mean maybe it's there. I don't know.
Yeah,
So it'd be interesting.
I don't know how deep in the design that gets. I mean, if you have like an input that you stuck at VCC or something very early on in your circuit, if you have a big system, I've never seen that warning for something like in the middle.
There's a connectivity checks reports after synthesis, RTL synthesis. And I know it at least gives statistics on the global inputs and outputs, but also it might give on a per module basis, things like that.
Yeah, so I've seen those warnings, but I'm saying I've never seen them in like the middle of a larger design. Like I don't know if it's really going like really checking formally into like.
Yeah, it traces the source of it.
Really?
Yeah, so if the output socket 1, it's because something inside the socket 1. All the processes
But
lead
you
to
could have
it.
something inside second one not affecting it.
Oh,
It doesn't get found, right?
maybe. I'll follow up on that.
Yeah, I would be surprised because it probably, there's very specialized tools that do this kind of stuff, and perhaps they're licensing it from someone, but I'm not sure about that. But yeah, I mean, all these kind of weird issues, you really, well, I don't know. I think you really, if you really care about functional correctness, you probably should be doing these checks as a sign-off before you send it to a physical design or, well, I don't know how it works in FPGA land, but I think these are very important. So, as I was mentioning before, System Verilog has a lot of these features. And it was first introduced in 2002, but I think in 2008 or 2009, it subsumed the regular Verilog standard. So there's only one standard now, System Verilog, that encompasses Verilog also. But the really interesting stuff is that it borrowed a lot of concepts from previous proprietary languages, I think such as E and thing, I'm not sure, I think E and maybe another one, that were developed and that were really best practices at the time. And they finally standardized it, which was really good because now it's supported across every major EDA tool. And so it has all these really good things like constrained random stimulus generation assertions, coverage. It has an object-oriented programming model, which is going to really promote reuse of the verification IP that you're making. And it also has plugins so that you can plug in C or C++, your C or C++ model into your test bench and run it at the same time as your RTL simulation. So it really has a lot of new features, which is kind of state of the art. And so I think that's why a lot of people are moving to System Verilog just for the support and for the fact that it has all these features that are really best practices in the industry today. Okay, so this is a kind of an open source library that you can think of kind of like the STL for writing assertions. So assertions, as I mentioned, really complicated language. There's so many subtleties, so many places where you can get it wrong. But this kind of just provides a library, and all you have to do is instantiate a module essentially and pass in the right parameters, and you have an assertion written. So it's supported by all major simulators. And it has, here are some examples of things you can write, like assertion to check increment, overflow, transitions, parity, and just really simple stuff that you have assumptions of in somewhere in the middle of your design, but you're probably not checking explicitly. So we have an example here that I took from somewhere that you never want more than one grant. I guess this is kind of a grant on a bus or something. And you basically just instantiate this module with these parameters. I guess these are kind of the bus width or whatever, and you pass in the signals that you want, right? So it's pretty simple. I mean, it's basically just instantiating a module, and it'll basically do all the checking for you. And a lot of people have looked over the code, so it's probably correct. You want a really quick way to start using assertions. This is probably a really good starting point. The next thing is this unified or open verification methodology, UVM or OVM. I think UVM subsumed OVM recently. So OVM, I think, was only supported by Cadence and Mentor Graphics, and Synopsys had their own thing. And then finally they got together and said, well, let's standardize everything, and they wrap everything into UVM. But basically, this is a standard framework for doing coverage-driven functional verification. And so, well, the methodology employs kind of all these ideas: test generation, self-checking test benches, coverage metrics, things like that. And what it really does is it promotes reuse and transactional level modeling through a framework of object-oriented base classes in System Verilog. So it tries to standardize the interfaces between these different components, standardize the framework of which you're building your test benches. And it has a bunch of things to help you do that, like transactions for your data structures, drivers, driving your design under test, sequencers, higher level, transaction level, input generation, monitors to check what's coming off the bus. There's a lot of different things that really, the best practices, 10 years people were using this kind of best practices, but only now have they developed the framework so that people can learn it more easily and apply it more easily too. And I think this kind of may be silly to you think, why do they develop a framework for this? But I think it really helps along in that whole adoption thing. I think adoption, even though we have all these new tools and new processes, adoption is really a big issue. So once it becomes standardized across simulators and vendors, now we can start giving courses and teaching one thing to all these hardware engineers who have been doing it for like 30 years. But now we can teach them kind of to do it in a more methodical way that will have a higher chance of catching bugs. Okay. I think I have a picture here. So let's see, what is this picture showing? We have the design under test over here, and then maybe a bus with some things attached. But basically, this would be this big box up here is our test bench, and we have all these different components attached to the bus. So I guess at the bottom we have these monitors which are checking the values coming off the bus. We have these drivers which are directly driving values on the bus. And the drivers basically will translate what these higher level packets of information that are coming in from the sequencers. And then I'm not too familiar with all the other things, but basically this is kind of a more structured approach to designing your test bench, and it kind of looks like something, it almost looks like a hardware design, I guess, in some sense. And it should. Your test bench should be a structured piece of software. It shouldn't be just kind of random, whatever you felt like testing thing, right? So UVM, there's a lot of documentation on UVM. The standard, I think, is free. You can go to accelera.org and find it all. So there's tons of examples online too, if you want to start looking into this. The next part I want to talk about is emulation. And so this is an interesting part I mentioned before that actually I want to say is replacing a lot more of FPGA prototyping. So I think a lot of you are familiar with one segment of the market of FPGAs. A lot of people, before they put it on their ASIC, they're going to put it on an FPGA, make sure it's running correctly. And you can run, not quite at speed, but a lot faster than you can do an RTL simulation. Now, from my understanding, a lot more people are moving to this emulation. And emulation is really just this big, expensive box that accelerates, runs your RTL faster, essentially. And so it's very specialized hardware, and you load your whole hardware design on this huge emulation box. And it provides the same benefits as FPGA prototyping, but I guess maybe a little bit easier. That's my intuition. And so, we're going to megahertz simulation speed versus hertz. And one of the key factors here is that we're able to simulate software on it. And so what that means is now we can boot Linux on it, and we actually really can find difficult bugs that otherwise is impossible to find in RTL simulation, right? And we can also verify our software is working correctly too. So I pulled this off the website, 100 million plus gates. Who knows how close that really is. But one cool thing is that you can actually accelerate some of your test bench code too. So you can reuse some of the stuff you used in RTL verification just to show that it's working properly. And I have two examples of boxes from Mentor Graphics and Cadence down here. But one of the big issues here is it's still very difficult to debug. And actually, you might think, yeah, it's running for millions of cycles and it's going to be hard to find the bug. But as I've heard, one of the biggest issues with emulation is just setting it up properly. Because it uses a different model of how it simulates, when you load your design on and run a really simple test vector and make sure all the outputs are matching compared to your RTL simulation, frequently what you get is a mismatch. And now you got to freaking debug this really complicated piece of hardware, figure out which configuration is wrong. And generally it's probably something really stupid, but still you spend days, I guess, trying to figure out and load this emulation box. And then I just put one slide in here about debugging, because that's kind of what I do. But I just want to talk about how you can make debugging easier. And I think there are really two schools of thought here. One is a methodology perspective. We have to have better design practices, code reviews, unit tests, things like that, to reduce the number of bugs we're actually introducing. More checkers, more places to check so that we can catch bugs earlier and debug them faster. And find bugs earlier in the design flow. We want to find all of them as much as we can as RTL simulation, then as many as we can in emulation, and then maybe find the leftover ones in silicon. And then the second school of thought is basically we need better tools. We've got to have different tools for different types of debug problem, and you've got to use the right one. We have source level debugging, transaction level debugging, constraint debuggers, hardware, software code debugging. And then this is really what I do, more automation in these tools so that we can debug faster and with less effort. I think most people would agree that it's really, what you really need is a combination of both of these to actually improve debugging. Okay, so I think that's the last slide on the tools and techniques part. And now I'm just going to talk about some methodology and process stuff that I found really interesting. And I don't think will be very surprising to most of you. But let's take a look. So the first thing is something that really has been adopted really quickly in the software industry. Basically unit tests and integration tests and system level tests. And the idea is not too complicated. We have, first of all, at the block level, whatever our smallest unit of module or whatever it is, we should be having unit tests to exercise that block level functionality. And then once we have more than one block, let's stitch them together like this and exercise the interface and assumptions that we made when we were designing those individual blocks. And then once we have, and this integration part is not just kind of one step and then you go to system. You can have many different levels of integration. You probably should. And then you can have a system level test that isn't trying to test individual bits, but really trying to exercise the use scenarios or use cases of the entire system, making sure it works correct. And if you design your verification environment well, what you can do is use a lot of the IP, verification IP that you have up here in the integration tests. So while you're running the integration test, you're also checking the same functionality you had when you had the unit tests. Similarly at the system level, if you design your unit integration test well, you can strap them on and also check for those same things in the system level test. Really, really increasing the number of points you're checking and increasing the chances of finding a bug. And the last thing over here is that usually we have something called regression test where we're really just testing a subset of test cases for previously verified or previously defined test cases to ensure that we didn't break anything when we make a change or maybe when we port a block to a new design, things like that. Okay, so this I think is not too surprising. So this is an interesting case. I'm going to show you the kind of answer to this next step. But this is I got this from a talk by J.L. Gray. He's a consultant in verification. And he says, he goes into companies and says, how can I improve your verification process? And this is, he says, this is a very common scenario, at least early on in his career, of what was happening. So an engineer will make a change. He verifies the change in the last known good build. At the end of the week or weekly, this integrator comes in and takes all the changes that have been committed and tries to run regressions. But the only problem is that the regressions don't work. Most of them will fail. And usually it takes 2 to 3 hours, up to a day, to actually fix that before we have a new known good build. And so if you think about a day, that's like 20% of the week where we don't have something that's working. So what are the common issues here? The merge build didn't compile or one or more regression tests failed. And this was caused by issues such as merges that were conflicting. They weren't validated against regression. You're missing files. And apparently missing files is a very common one too. And environmental differences between shells, right? So this is kind of really stupid issues. We shouldn't be spending 20% of our time not having a good build just because of these stupid issues. And he said, it was funny, he claimed that, I'm going to tell you how to increase your verification efficiency by like 100% or something like that, just by doing one thing. And then that one thing's on the next slide. Can anyone guess what that is? No? But I think you guys all know what it is. It's called continuous integration, where basically you have some of these really simple concepts. The head of the trunk or your main line should never be broken. And you want to make sure it stays healthy. And so one thing I didn't put on here is that every time a commit happens, you should be running a small suite of regression tests to do some sanity checks on whatever was checked in. But basically, the idea is you want to fix broken tests in the main line as soon as possible, when they should be running basically on every commit. And the important part over here that he was stressing is that you need to get team members on board. If there's half the team is not on board with this continuous integration idea, the trunk is still going to be broken maybe half the time, right? So you really need to get process or everyone on board to do that. And the idea here is that this is kind of stuff that we've done in software for many, many years. We should be using branches to commit unfinished or broken code or feature branches to do your work in. And then once you're ready, once your feature is ready, merge it back into the main line as quickly as possible so that we can make sure that the integration is not broken, right? So this is kind of one thing you can do to increase your verification efficiency to like 100%, right? Now, the next question over here is, the question I was asking at the beginning, you verify your RTL, you run tons of simulations, how do you know when you're done, right? So there's no clear answer to that. Many people have different strategies, maybe based on experience or whatnot. But one interesting thing from this Harry Foster survey over here is that more and more people are biasing towards this coverage when our coverage says we've reached a sufficient amount of coverage. We've reached some kind of milestone in coverage. Then it's time to ship my RTL and send it to physical design. And you can see in 2012, this has increased from 20% to 25%. So really, people are starting to see the benefits of using a coverage-based approach. Now, I don't know what these other things are doing, but I guess most people are saying when my verification plan is complete, but depends, I guess, how good their verification plan is, right? And the last topic I want to talk about is this really interesting talk I heard at the DV Club, but I think this was presented at DVCon too. And this is an idea borrowed from software development research. And they basically use this Rayleigh model distribution to predict the number of bugs found. And it's basically based, there's I think two main parameters, the number of lines of code you have, and also how long your project is going to exist. So you can use historical data from previous projects to set these parameters. And what's interesting is the guy who was talking was from Sun Microsystems, or now Oracle. And he basically, with this model, achieved a 1% accuracy within the actual bug rate. Like his model predicted within 1% the actual bug rate. And so this can help you answer a lot of these questions like, well, when is it time to actually stop RTL simulation and start putting things on the emulator? Maybe when 75% of the bugs are found. And another one is when do I do a freeze process, and maybe when 90% of the bugs are found. So I have two interesting graphs that shows about this. This one is, so the blue line is what the model predicts. And so you can see kind of the smooth curve over here. And this is the black line is the actual line. I think this is from one of his projects. So you can see that at some point, the black line really doesn't model the blue line at all. But it turns out, one of the reasons is because you had this test bench bug over here. And so after the test bench bug, it starts following the curve relatively well, which is interesting. And then I think this is from another project he did, UltraSpark processor, I guess. And you can see the blue line, again, is the predicted one, and the red line is the actual curve. So he did a pretty good job in terms of, at least for this project, he modeled it pretty well so that he can make pretty good decisions on at what point or how many bugs we've actually found. And I think that's all I have. Yeah.
Thank you.
Jason? Yeah.
So modern designs today use a lot of third-party cores. Some of these cores might be encrypted. How do you see this affecting debug and verify?
Yeah, so that's actually one really big issue with debug. Not only they're using third-party cores, but they may be using legacy cores that the designer who wrote the core is not around anymore. And so what we're seeing today, I think, is, well, we have to use all the techniques I talked about, but a lot of the times, these cores are we start having two things. One, verification IP attached to these cores to ensure that they work. And I think a lot of the better IP core vendors will give you kind of a test suite to ensure that under these assumptions our core works properly. The second thing is you see a lot of vendors now, Cadence and Synopsys, making verification IP and selling verification IP. Like you're making a USB 3 block, I have verification IP that will check it. All you have to do is run it through my verification IP, and if it passes everything, you can be sure your block is working. So there's this big movement, I think, just because of the massive size of the designs, to start reusing a lot more, and that might include buying design IP, and also verification IP. Yeah.
So in FPGA design, post-silicon debug is certainly a lot cheaper than actual ASIC or
Definitely.
VLSI design. And we actually have tools available to us that the ASIC people don't have access to, such as SignalPath 2, which lets us probe into our actual design
Yep.
and see it happen in runtime. How do you see this affecting the debug methodology for FPGAs?
Well, I think, my intuition on it is that in FPGA land, you guys really haven't hit that wall where it just starts getting impossible to debug. And I think that's one of the reasons why a lot of people haven't shifted over to doing RTL simulation at the RTL level. But as that one of those slides show, I think there's an increase of people who are doing that, and that's most likely just for necessity. You know, doing simulations RTL level, setting up these complicated test bench does take time, and I guess the trade-off in time is just starting to hit the breaking point for some designs, which maybe are really big, really hard to debug. So they're doing the simulation RTL level to prevent future bugs and debugging at the silicon or FPGA level.
I think some of that's kind of cultural too. I mean, if you are brought up as an FPGA designer, you have this mentality I call debugging like an undergrad, right? You keep recompiling it until it works. But when I had my startup company, all the people I hired were all ASIC designers, right? And so they had this mentality like, this is the way you do it. You don't do it any other way. And so we have experience of bringing up like monster boards, and we brought them up in like 2 hours. Right?
Wow, that's pretty impressive.
And, you know, the guy who was managing the hardware group, who was from Nortel, said, you know, he would have thought it would take us 2 or 3 months to do that. But we had this entire simulation methodology down with multiple FPGAs, and we simulated the heck out of it. And as I said, the board came back 2 hours later, it was plugged into the system.
Yeah, I think that really stresses a point that, you know, a lot of this culture or resistance to new methodologies, and I guess FPGAs have their own kind of historical resistance too, because maybe a lot of people just run it on the board and see what happens, and probably it's okay for an undergrad project, but maybe not so good when you're shipping something to a fighter jet or something, right? So,
Okay, so we're just delaying, we're waiting for the pizza to show up, which hopefully will be any time now.
oh great, it uses up the whole hour, right?
Yeah,
Almost.
that was good. Okay.